This video is a very brief introduction to polynomial functions. We'll begin with the definition. This is a typical mathematical definition. We'll go through it, then we'll pull it apart. We'll use some examples to see exactly what it means. So, a polynomial function of degree n is a function that can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a sub 0, where n is a non-negative integer and each a sub k is a real number with a sub n not equal to 1. So let me say a few words about this first. This dot 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 means that the pattern continues here until we get down to a sub 0 all by itself. N could be, it's a non-negative integer, which, remember, is a whole number or the negative of a whole number, except this can't be negative because it's non-negative, which means it's a whole number. It's 0, 1, 2, 3, etc., etc. Now, if n is 2, it doesn't actually expand to all of that, and it'll actually look more like just the tail end of that. But that's okay, the dot 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 can encompass that. I've just written it out enough here to establish the pattern really well so that we can get used to working with this sort of notation. I also want to point out a sub n cannot be equal to 0, but any of these other a sub k's can be. It's a real number, or each of them is a real number. 0 is a perfectly good real number, so we might have that be the case. Alright, let's look at a specific example. So notice this is just the equation from the definition. I just want to keep that up on every slide so that we can continue to refer to it. And our example is a polynomial of degree 5. Remember, this definition is for a polynomial of degree n. So my 5 is n. And here is my polynomial. 3x to the 5th plus 17x to the 4th minus 54x cubed plus 12x squared plus 4x minus 71. Now I'm asked to identify certain parts of this polynomial. Notice the first thing I'm asked for is n. N, as it says in the on the prior slide, is the degree of the polynomial. N is the highest exponent. Notice that my pattern that's established is I start with n, and then as I go on, I keep subtracting from that exponent. So my highest exponent here is 5, which is also the degree, and so that's what n is. A sub n is the number that goes in front of x to the n. So I could also refer to this as a sub 5, since n is 5 for this example. And in this case, a sub n is a sub 5, which is 3, the number in front of x to the 5th. The next thing I'm asked for is a sub 0, or we say a naught. That here is the last lonely little thing all by itself. If I look at my specific example, negative 71 is playing the role of a naught here. A sub 1 is the number in front of x, and so that, according to my example, is 4. A sub 2 is the number in front of x squared, so that is 12. A sub 3 is the number in front of x cubed, and so that's negative 54. Let's have another example. So here is the definition again. And here is my specific example. I will notice that I've got x to the 7th, well, I've got 1/2 x to the 7th, but 7 is my highest exponent. I do have this written in descending order, which is sort of the nicest way to write your polynomial functions. But 7 is my highest exponent, and so that is the degree of this polynomial. And now we have a batch of questions about this polynomial. So at this point, you should pause the video, try to answer these questions for yourself, and then unpause, and we'll go through them together. So I'll assume that you have paused and unpaused now. N, again, is the degree. It's the highest exponent. In this case, that's 7. A sub n is the number in front of x to the 7th, so that is 1/2. A sub 0 is my last term without an x at all. That's 8. A sub 1, well, now if we look at this, there's not really a number explicitly written there. I've got minus x, but if I were to force a number to appear there, I could always write that as minus 1x, and so a sub 1 is negative 1. A sub 4 is the number in front of x to the 4, and so that's a negative 94. And a sub 2, well, notice it should be the number in front of x squared, but I don't have an x squared. Now I could force something with an x squared in it to appear in this polynomial if I were to say plus 0x squared, and a sub 2 is therefore 0. I want to remind you that a sub n can never be 0, because if it were, this wouldn't actually be here, and my highest real exponent would be 6, but any other a sub k can be 0. All right, one more example like this. So take this and, well, let's answer the polynomial of degree. My degree is my highest exponent, which is 16. And now pause again to answer the rest of these questions. I will assume you have unpaused now, and so n, notice that nothing actually shows up in front of x to the 16, but I could write this as 1x to the 16. That would have the exact same value that this does. So my, n is 16, a sub n is 1. A sub n is the one I was talking about. A sub 0 is my little number here all by itself. That is negative 1. And then, well, notice there's not a whole lot else going on in this function. A sub 1 is 0. A sub 14 is 0. A sub 8 is 0. You could write in a term for every single number in between 16 and 0. By having a whole lot of 0x to the 15th plus 0x to the 14th plus 0x to the 13th and so on and so forth. But it's enough to just recognize that all of those are 0. So let's look at some functions and determine whether they are a polynomial or not. So I've got 3 functions here. I want you to pause the video, take a look at these 3 functions, and see if you think they meet the definition. Alright, so let's look at this first one. I've got 8x to the 2.5 minus 3x to the 1.5 plus x to the negative 2. Well, it has some qualities of our pattern, but our exponents have to be non-negative integers. 2.5 is not an integer. Negative 2 is an integer, but it is, of course, a negative integer, so it doesn't meet the qualifications either. Now, here I will point out that each exponent failed this particular test, but having one single exponent that fails to be a non-negative integer is enough to make the function not a polynomial function. It could still be a function, and a very interesting function, but it would not be a polynomial function. So now let's look at g of x. I have pi x to the 8th plus x times the square root of 3. Well, I've got, remember, pi is a number. It's approximately 3.14. It's not exactly 3.14, but in any case, it is a number times x to the 8th plus a number times x. We typically, when we have a radical like this, write it as the last little piece whenever possible. That way there's no confusion as to whether that x is underneath the radical bar or not. This is a polynomial function. Pi is a real number. Square root of 3 is a real number. My exponents all are fine. Both, I should say, are fine. And so that is a polynomial function. Even though you might feel a little uncomfortable with a polynomial function that has a pi in it, it is still a polynomial function. And then finally, this looks nothing like our definition, but remember that definition said that the function can be written in that form. I could multiply all of this out, and I would get something that very clearly looked like the polynomials that we're used to working with. So when you multiply this out, it is clearly a polynomial. So that can be written aspect of that is important. This is still a polynomial function. I have a few interesting facts about polynomial functions here. The graphs of polynomial functions are always continuous and smooth. I'm sneaking in some vocabulary here, but we'll just go for a nice intuitive understanding. A function's continuous if you can draw the graph of that function without picking up your pencil. So any kind of jumps or breaks in the graph would be a discontinuity. Polynomial functions are always nice and continuous. They are also smooth. They might wiggle a lot, but they won't have a jagged corner the way, say, the absolute value function does. Another interesting fact, the zero function, which is f of x equals 0, that is a polynomial function with no degree. That feels sort of weird to say that it has no degree, but, well, there you have it. Any other constant function is a polynomial function of degree 0. And by constant function, I mean f of x equals a constant. F of x equals 5. F of x equals 102. F of x equals negative pi over 16. Any constant function is a polynomial function of degree 0. Every linear function is a polynomial function of degree 1. Remember, a linear function is a function whose graph is a line. And every quadratic function is a polynomial function of degree 2. Remember, we introduced the term quadratic function when we introduced our common functions in our function transformation module. A quadratic function the simplest quadratic function is the square function, y equals x squared. That is a polynomial function of degree 2. And we have a few more vocabulary words I want to introduce. I've put up our definition again so that we can refer to it. Each a sub k x to the k, each one of these things that is connected by addition is called a term. So you'll have a bunch of terms inside a polynomial. A sub 0, a naught here, is called the constant term. Each a sub k, each number that is in front of the x to the whatever, that's called a coefficient. And a sub n is the lead coefficient. And it's just the coefficient of the term whose exponent is to the degree of the polynomial, that highest exponent. And that concludes our very brief introduction to polynomial functions. Now, a friend of mine thought that we needed some music to sort of conclude these videos, so enjoy the theme song written by Doug Ray of Texas State University.